Alrighty guys, so today what we're looking at is exponential functions. Okay, so we are going to understand the structure and key features of exponential functions and use them to model growth and decay. So an exponential function, I can't remember whether we looked at these last year in year 10 or not, but I think we maybe ran out of time. So an exponential function is in the form y equals a to the power of x. This is where a is greater than 0 and a cannot equal 1, okay? So a never starts at 1, but it's going to be greater than 0. What we have for an exponential function in the form of y equals a to the power of x is it has a domain of negative infinity to infinity. It has a range from 0 to infinity, okay? We have that the y-intercept is always going to be 1. This is because a to the power of 0 is in fact 1, because anything to the power of 0 is 1. We have that with our range, is 0 to infinity. So that's telling us that we have an asymptote at our x-axis. Now with our graph, and we'll look at how to graph one of these in a short moment, we have that the graph is always above the x-axis due to that asymptote, and there is no x-intercept. This is because a to the power of x is greater than 0 for all values of x. We also have that y equals a to the power of x is monotonically increasing function unless a is a fraction where 0 is less than a is less than 1, then it's monotonically decreasing. Now, if it's monotonically increasing or decreasing, it means it's always going up, okay? We will have heard about exponential growth and decay maybe. So like when COVID was a thing, we had exponential growth in cases, so the cases rose really quickly, and we'll look at some cases like that. Now, we'll jump back to filling exponential functions y equals k a to the power of x in a second. But what we're going to do to start off with is we're going to have a look at how to sketch the following functions and state their domain and range. So for our function fx equals 3 to the power of x, we have that our y-intercept is at 1. So at 1, we're going to have a y-intercept there. Okay. What we then have is when x equals 1, what do you think y equals? 3, right? When we sub in x equals 1 here, we have 3 to the power of 1, and we know that 3 to the power of 1 is just 3. So we're going to put a dot there. Now, if we substituted in x equals -1, 3 to the power of -1 is a third. So what we have with our function is our function never touches our x-axis, and it's increasing like so. So it's always monotonically increasing, and it's going up and up and up. Now, at x equals 2, y would equal 9, and I haven't provided that we need to show that on our graph. So what we just have is we have the point 1, 3 there. Okay, we need to make sure that when we're sketching this function that we show that point, we have arrows on either end, and we show where our y-intercept is, and then we need to label our graph fx equals 3 to the power of x. Now this function is going to go on and on and on for all of our domain, so that means that our domain is negative infinity to infinity, and our range is from 0 to infinity because we have that asymptote there. Okay, you don't need to draw the asymptote on, you just need to know that it exists. Any questions about sketching the exponential function fx equals 3 to the power of x? No? Now our next one here, we have y equals 2 to the power of x plus 1. So what we have with this function is it's the function y equals 2 to the power of x, but what that plus 1 does is it vertically translates it 1 unit up. So it's vertical translation 1 unit up. So what this means is we will have our asymptote is usually at y equals 0, but if we're moving our whole graph up, our asymptote is now going to be at y equals 1. Okay, so at where 1 is where our asymptote is going to be. Now, what we have is our x-intercept is not going to be, we have no x-intercept. Our y-intercept, when we find our y-intercept, that's when we let our x equal 0, right? So we'll have y equals 2 to the power of 0 plus 1, which is y equals 1 plus 1. So y-intercept is equal to 2. We don't have to do that working out because we know that our y-intercept is going to be at 1, but because we've shifted it up 1, 1 up from 1 is 2. So we'll have our y-intercept at 2. Now, the other thing that we need to find out is when x equals 1. So when we substitute in x equals 1 into here, we get 2 plus 1, which is 3. So at 1, it's going to be, nope, that doesn't make sense. 2 to the power of 1. Yeah, that's 3, isn't it? Yes. Yep. It's going to be at 3. Okay, and then if we were to substitute in 2, we would have 2 to the power of 2 is 4, plus 1 is 5. So at 2, it's going to be at 5. Okay, if we were to substitute in -1, when we substitute in -1, it's going to be at 1.5, if that helps. But we don't need a lot of points. We just need our y-intercept and 1 key point. Okay, that is why I have given you a graph that has no other values on it. Because when we have other values on our graph, what we need to do is we need to make sure that we're drawing it accurately, okay? But because we don't have any other values on our graph, we don't have to draw it as accurately. We just need the general shape and those key points of our y-intercept, our asymptote, and a key point on our function. We also need to make sure that we're labeling our function y equals 2 to the power of x plus our 1. Now, this is where our domain and range has slightly shifted, okay? Well, our domain hasn't changed. Our domain for an exponential function is always going to be -infinity to infinity, always, no matter what we're doing to it, okay? But our range is now where our asymptote is. So our range is 1 to infinity. Okay, so whatever our asymptote is, on the first one, our asymptote was at y equals 0. For this one, our asymptote is at 1. So that is what's going on there. Now that we've looked at what the general shape of an exponential graph looks like, we're going to scroll or look back up at an exponential function's y equals k a to the power of x. So what we have is our k value. It affects the height of the curve. Hopefully you have enough space to write the word height in there. I'll just tidy that up. It affects the height of the curve compared to y equals so what that k does is affects the height. So it's either monotonically increasing or decreasing depending on the sign of k and the value of a. Okay, we have that the domain is always going to be -infinity to infinity, but our range is going to change, okay, depending on what is going on here. We have our y-intercept is always k. So whatever the k value is out the front is going to be our y-intercept, and this is because a to the power of 0 is 1, and we're timesing that by k. We have that the x-axis is still an asymptote, okay, unless we translate our graph up or down. Okay, even if we translate our graph left or right, our asymptote is still going to be at our x-axis. Now, when we have k is greater than 0, so when we have k is positive, Our domain is going to be that negative infinity to infinity, and our range will be that the function is above our x-axis. So our range will be 0 to infinity. So when k is greater than 0, the graph is always above the x-axis and there is no x-intercept, because a to the power of x is greater than 0 for all values of x. Now, what we have is some limiting behaviour notation here. So what we have is as x approaches infinity, so that little triangle, an arrow means approaches, if you weren't sure. If you are sure, you don't have to write that down. So that arrow means approaches. So as x approaches infinity, so as x gets larger, y is also going to approach infinity. So that means that y is also going to get larger if our a value is greater than 1. And then what we have is as x approaches negative infinity, if we look at these graphs, so as x gets smaller and approaches negative infinity, what we have is that y approaches 0. Okay, so it's never going to touch 0, okay, but it's approaching it. This only changes if what our k value is. Now, for our k is less than 0, that means it's a negative k value. Our domain is negative infinity to infinity. But what the negative k value does is it flips the graph to be under the x-axis or below the x-axis, meaning that the range is negative infinity to 0. Okay, so like I said, the graph is always going to then be below the x-axis and there is no x-intercept, because a to the power of x is greater than 0 for all of x. Again, we have as x approaches infinity now, we have that y will approach negative infinity, and we have as x approaches negative infinity, y approaches 0. Okay, flip the page when you are ready. We have a few more to sketch. Four more to sketch. I wanted to show you all the options and what happens, okay? They're pretty easy sketches to do. Okay, our first one, what we have is to sketch the graph of fx equals 3 to the power of 3 lots of 4 to the power of x. So what this means is that the values of f of x will be 3 times higher than if we were just to sketch 4 to the power of x, okay? And so the curve will then be steeper for this. So what we have is our x-axis is going to be our y-intercept is our k value. So our y-intercept is going to be 3. Now, something we want to think about is what is our value going to be when x equals 1. So when x equals 1, what is y going to be? 3 lots of 4 to the power of 1 is 12. So when we have it equaling x equals 1, we want 12. So we can go up 3, 6, 9, 12 and have our point there and have our point on our y-intercept at 3. Now, like I said, all we need is the y-intercept and a key point. So when we sketch this curve, it is very steep, but that is what we want. We want to show that it's nice and steep. We want to put in a dot 1, 12 at that point. Okay, and we want our fx equals 3 lots of 4 to the power of x. It is really steep. Okay, you can also find out other values, but it's not worth finding out other values up above. Okay, because otherwise you're going to draw it really big. Our domain stays as negative infinity to infinity, and our range is 0 to infinity, okay, because we still have our asymptote. at y equals 0. Yes. Okay. Our next one, what we have with our next one is it's y equals 2 to the power of x plus 1. Now, how do we sketch a function if we're unsure? What can always help us sketch a function? Table of values. So if we weren't sure about this function, we could definitely do a table of values. In fact, that's what we could do in our head. So our y-intercept is when we have x equals 0. So it's going to be y equals 2 lots of 0 plus 1. So that is y equals 2 to the power of 1, which is just 2. Am I good just to write y equals 2 there? Yes? Okay. What we can then do is we can find out what's happening at other points. So at other points when x, so we could even just draw a little table of values down below if we'd like. So we could do -2, -1, 0, 1, and 2. Okay, so we already know that it's at 2 when x is 0. When x is 1, it's going to be 2 to the power of 2, which is 4. When x is 2, it's going to be 2 to the power of 3, which is 8. Now, when x is -1, it's going to be 2 to the power of 0. So that is 2 to the power of 0 is 1. And then when x is -2, it's going to be 2 to the power of -1, which is a half. Okay, so we have the general idea of what's going on. Based on my y values, I'm just going to go up by 1s for my y-axis. Okay, go across. You can also, if you want to stretch this out a little bit, you can do that. You leave a dash and you do 1 and 2 separate. So what I mean by that is you'd go 1 here, 2 there if you wanted to, but quite happy for it to be nice and skinny if you like. Okay, so if we plot these points, so we have our y-intercept at 2, at 1 it's at 4, at 2 it's at 8, that's off our graph, that's totally fine. At -1 it's at 1, and at -2 it's at a half. So we get the shape of our graph. That's not very good. All right, and it's a nice smooth curve. I like to maybe draw the points that I have and then put my tail on the end. Okay, we want to make sure that it's clear what our y-intercept is, and it's also clear what one of our points is. Now, we could pick any of the points. We could write -1, 1. We could also write 1, 4 as well. Okay, so when things are up and attached to our x, that's what we can just do for it. Our domain is still -infinity to infinity, and our range is still 0 to infinity. Okay, nothing's changed with our range there. Ooh. The next one does look a little bit tricky, and I just realised I didn't show you one that I was going to show you. But anyway, what we have for E is we have our y equals -3 to the power of x. So what the negative means is that we have a k value less than 0. So this means it's going to be below our x-axis. Okay. What we're going to have is we're going to have our y-intercept. I might just do it down here. Our y-intercept is going to be -3 to the power of 0 is actually -1. Okay, so at -1, we're going to have it there. I'm just going to find out what happens at 1. So at 1, it's going to be at -3. Okay, and so what's happened is it is flipped like so. Need to put some numbers on. I was just seeing where things fell. So -1, -2, -3. That is the point 1, -3. Need to write my function. So when we have k is less than 0, so there was a negative in front, what we have is that it goes below our x-axis. Does that make sense? Yeah? Okay, this is also called, when this happens, It's called a reflection in the x-axis. Because what we have done is our original function that we sketched, y equals 3x, we have reflected that in the x-axis. Okay, that terminology will help us when we look at transformations of functions. Our domain hasn't changed. Our domain is still negative infinity to infinity, but our range has changed now. Our range is now negative infinity to 0. Okay. Our last one here, what we have is y equals 3 to the power of negative x. So what that power of negative x does is that is going to reflect our graph. It's a reflection in the y-axis. So instead of our graph looking like this, right, what our graph is going to be is it's going to be reflected in the y-axis and it's going to go that way. But let's sketch it properly. So what we have is we still, when we substitute in x equals 0, we're still going to get a y-intercept of 1. Okay, but when we substitute in x equals 1, we're going to get a third. When we substitute in negative 1, that is when we will get our value at 3. Okay, so we can then sketch our curve like so. Put our values on 1, 2, 3. Label that point as negative 1, 3. Make sure it's obvious where your y-intercept is. If for some reason you've drawn over the 1 value for your y-intercept, you could put a point there and write 0, 1. So that's nice and clear. And we need to also make sure that we label equals 3 to the power of negative x. Okay. So all we've done is we've picked it up and we've flipped it about the axis. Now, our domain is still negative infinity to infinity, but our range is also going to be 0 to infinity because we still have that asymptote at x equals 0.